this whole thing is inside. So it becomes, this cancels with this. Sorry? Negative? Where did you get the negative from? Okay. So yes, negative a over 2. Yeah, okay. And plus pi. And this whole thing is multiplied by 1 over 2 pi, which ends up being half, right? That's the pi part when multiply, and then minus a over 4 pi, right? So that's the d0. And then you need to calculate dn. That's the tougher calculation. So that one is, again, you have the two, so 1 over 2 pi, and you have the two integration intervals. So you need to integrate from 0 to a. Your signal in that case is t multiplied by 1 over a, and then e to the minus j n. First of all, what's omega naught?
T is 2 pi, so 1.
Mm-hmm. 1. So omega naught is equal to 1, because omega naught, just let's write it by definition, it's 2 pi over the period, t, and the period is 2 pi as well, so it's 1. Okay, because this is 2 pi. It's already mentioned in the question. Okay. Okay. So you have, so e to the minus j n, omega naught is 1, so you don't need to put it there, and then you have t, okay, with respect to time, and then you integrate the other part from a to pi, and inside that part you have just e to the minus j n t dt. Okay. And now you need to solve these integrals. Again, the first integral is a bit lengthy because it includes t multiplied by e to the power t. And we know that this integral is typically solved by integration by parts. You typically integrate this part and differentiate this part. So you get rid of the t. So it's done in 2 steps, right? And the second integral is quite easy. It's just an exponential, okay? I'm not gonna go through the steps because otherwise the class is not gonna be enough, but I'm going to post the final answer for this to you next to the place where I put the tutorial itself. So you'll have the final answer for each one of those questions, so that when you continue the derivation, you can check versus that final answer.
Just
Okay?
the final answer with the steps as well.
Steps are up to here, and then integration by part, I mean, that's like calculus 2. Okay, so should be able to do it, right? But only I will post the final answer so you can continue. I will just say here, integrate by part. Okay, this part. Okay, so you know what to do in terms of solving the integral, and then do the derivations, and you will have the final answer to check against. Any questions about this question? By the way, when we talk about these questions and these problems, okay, so first of all, did we get something similar to what they have here for D0 at least? You already know the answer for this one, by the way, because it says show that Dn is equal to this. So you already know what's going to be the final answer, okay? So for D0, we got the same thing, right? This half is the first part. 2 pi over 4 pi is the half. And then we have a over 4 pi, right? So we got exactly the same answer. For the Dn, you should get the final answer that you see up there. So this particular question does not need posting the answer, but for the others, I will do so, okay? When we are doing those, if it comes across your mind when we are doing those tutorial questions, that there might be some variation that makes this not so straightforward or whatever, please feel free to ask these questions. So, doctor, what if this happens? How can I approach the problem? Feel free to ask this while we are doing the tutorial. So the idea here is not just me going through solving and that's it, okay? If ideas comes to your mind and you want to check against those ideas, I'll be happy to answer. I don't remember I recorded, but it's being recorded. I don't know how. Yes.
When we're doing by parts for that one part of the integration, you know how you do uv minus the integration of v du? Is that integration an indefinite integral or a definite
No,
integral?
no, with the same limits of the integration.
Because I've watched a video and they use an indefinite integral and then they evaluate the whole thing with the limits of the
It's the
integration.
same. This is going to give you exactly the same result.
Oh.
Because you integrate and then you substitute in the result the
Yeah.
upper limit and the lower limit, so that's fine. So the first part, once you got it out, so there is no integration, you can immediately substitute. And then the second one, you can put the limits. Once you solve the integral, you can substitute. The same as saying, I will keep everything until I get one final expression and then substitute on all of them. It's the same thing. Okay, any other questions? Okay, so let's go to the next question. It says that the exponential Fourier series of a certain function is given as, so this is the exponential Fourier series expansion. So what you see on the right side are the dn's multiplied by the complex exponentials, right? Remember, so these are not just the dn's, okay? Because remember we say x of t, what's the expression? Summation. Exactly. dn j n omega naught t, right? So now it's given to you in this form. That's what you have here. So this is d whatever, depending on what's the n here, and this is the other d, and this is the other d, and so on. Okay, so these are the d's, but they are already multiplied by their corresponding exponential terms. That's why this is written as x of t is equal to this equation. Okay? So let's remove those so we can see things clearly. And then it says sketch the exponential Fourier spectra. So what you need to do here is those dn's that you have here, you need to sketch them. Of course, to sketch them, you need to sketch magnitudes and phases. Okay? So let's see first of all, what are these d's? So when we look at this signal, what's going to be your impression about the fundamental frequency or the fundamental period about this signal? So we have e to the jt, right? Which means that we have something, so the lowest frequency that we have among all of those is what? 1, right? And negative 1. By the way, when we say the lowest frequency, we only talk about the positive. Okay, so whenever I ask you about, for example, what's the lowest frequency of a signal, don't tell me it's -3. Okay, it's always the positive side. The negative side is just an expression of mathematical completeness or mathematical correctness. But there is no such a thing like a frequency -1 or a frequency -3. Okay, so anyways, so the lowest frequency that we have here is 1. So we can safely assume that our fundamental frequency is the part that has a 1 to it. Okay. So our fundamental frequency here, omega naught, is equal to 1. By inspection. We didn't do any mathematical derivation or anything, just by inspection. Okay? And accordingly, we can immediately know that this is, this should be d what? Which n? d1. And this is d3. This is going to be d minus 1, and this is going to be d minus 3, and this term is d0, the dc term. Okay, so immediately we can figure out, first of all, which n each one of those coefficient corresponds to, and you can write them down if you want. So d0, again, you can just simply say here by inspection, and that's fine, totally accepted. Okay. So by inspection, we know that omega naught is equal to 1, and we know that d0 is going to be 3, d1 is equal to minus 2j, d minus 1 is equal to 2j, d3 is equal to 2 minus 2j, and d minus 3 is equal to 2 plus 2j. Okay, so now I know all the coefficients. I need just to plot them. So magnitude, so this is the magnitude of dn. I know that the locations are going to be 0, 1, and 3, and also minus 1 and minus 3. The other locations are going to have 0, so there are no coefficients there. D0 straightforward, it's just 3. It's a real value anyways, so the magnitude is known, and the value is 3. Now, D1, what's going to be the magnitude of that? Minus 2j. What's the magnitude of that term? It's straightforward. 2, exactly. So the magnitude is not minus 2. The magnitude is always positive. So if you want to do it, I mean, like the classical way, you say that the magnitude of D1 is equal to the root of the real square plus the imaginary square. The real square is 0. The imaginary square is 2 squared, right? And you add those together, so the result is going to be the root of 4, which is equal to 2, right? But again, by just looking at it, it's a pure imaginary term, so whatever is multiplied by the j is the magnitude without the sign. So it has a magnitude equal to 2, okay? So D1 has a magnitude equal to 2. And similarly, when you look at D minus 1, you will find that it also has a magnitude equal to 2. So the same thing here. We'll see later that the difference between those two comes from the phase term, not from the magnitude term. And then D3, what's the magnitude of that? So it's the root, so the magnitude of D3 is equal to the root of 4 plus 4, which is the root of 8, okay? What's the root of 8? Yeah, 2 root 2, which is how much? So it's 2 times 1.7, that's like, that's like 3.4, 3.5. So it's gonna be something a little bit higher than 3. And similarly on the other side, something a little bit. That's 2 root 2. 2 root 2, that's the magnitude value, okay? And the rest are zeros. So this is the plot of the magnitude. Now you need to plot the phase as well. So let's try to look at how we plot the phase of dn, okay, versus n as well. So this is versus n. 1, 3, minus 1, minus 3, okay? So for the phase, again, the DC term is just a real value, which means that it has a phase equal to 0. So there is no phase here. At 1, minus 2j. So a pure imaginary term would have a phase equal to
Pure imaginary.
yes,
Just
either pi over 2 or minus pi over 2, depending on whether it's positive or negative, right? Okay. So for that one, the minus 2j, it means that the D1, it means that this has a minus pi over 2 phase, okay? If you want to do it, I mean with the pure calculation, you know that the phase of D, let's say D1, is equal to tan minus 1, the imaginary over the real, right? So the imaginary part here is minus 2, the real part is 1, okay? And tan minus 1, 2 is equal to, tan minus 1, 2 is equal to,
Does it have to be in degrees or like
nah,
1.1?
which is what in terms of pi? It's half pi, right? It's pi over 2. Calculate pi over 2 and see whether it gives you the same value.
It doesn't.
No?
it's tan inverse of -2, right?
Yes, and 2 here is radian.
Yeah.
Yeah.
And then when I do 1/2 pi, it gives you 1 pi.
No, it's pi over 2.
Yeah, 1/2 pi.
1 over 2 pi? 1 over 2
Yeah.
multiplied by
Yeah.
pi. Yes. Yeah, sorry. This is wrong. The real part is not -2. The real part is 0. Yeah. So tan -1 infinity is what? So which angle gives you infinity? It's pi over 2 and minus pi over 2. Which one you pick, the positive or the negative, depending on the sign. So sorry, I made a mistake here by that one. You were right. Okay? So the angle here is pi over 2 with a negative sign because you have a negative sign here. Okay? So this means that for 1, you have negative pi over 2. When you look at d minus 1, same thing exactly. So it's tan -1 of 2 over 0, which is an infinity, and that's either a pi over 2 or a minus pi over 2. Because this is positive, it's a pi over 2. So the angle here is pi over 2. Let's check the next one. D3 and D minus 3. So D3 is 2 minus 2j. You either again do it by the calculation, and you'll end up tan -1 of 2 divided by minus 2, minus 2 divided by 2, which is tan -1 minus 1. Okay? It's the inverse tan of -1. Okay? And the inverse tan of -1 is pi over 4 with negative, right? That's 45 degrees, okay? Or by inspection here, you have the same value for the real and the imaginary, so this must be aligned at 45 degrees, either positive 45 degrees or negative 45 degrees, okay? So anyways, the angle of D3 is equal to tan -1, imaginary over the real, so -2 over 2, and that's tan -1 minus 1. And by again, you have a negative imaginary and a positive real, so that's a -45 degrees. That's minus pi over 4. So you have here at 3 minus pi over 4. And similarly for D minus 3, it's symmetric from the other side, but anti-symmetric. So again, it's pi over 4. So that's the sketch of the magnitude and the phase of the spectra. And then it says, after sketching the exponential, so now we sketch the exponential. It says, by inspection of the spectra in part A, sketch the trigonometric Fourier spectra of x of t, and find the compact trigonometric Fourier series representation. So how do you do that? How do you get the trigonometric from the exponential? Let's do the compact one, for example. So you remember there was a table that gives you the relation. It was in the Fourier series lecture slides, right? And it's in the book as well. And in that it says that the compact trigonometric parameters are Cn and theta n, right? And the representation is x of t is equal to the summation from n equals 0 up to infinity, so it doesn't have a negative side. Cn, right? Cosine, or a more classical way, just let's follow the classical way. It's C0 plus summation from n equals 1 up to infinity, Cn multiplied by cosine.
What's the difference between Cn and Tn?
Cn is called the compact trigonometric representation. So now we don't have complex exponential in the equation. It's all cosines with phase shifts, the theta n.
Okay, so Cn is Dn, but with the trigonometric part.
Yes, yeah, it's not going to be exactly the same. I will remind you the relation between them now, but I'm just writing the expression right now. So it's cosine n omega naught t. Unfortunately, you are getting out, so plus theta n. Right? So you have cosines now at different, sorry? N omega naught t, yes. So at every n, you have the multiples of the frequency. So you have cosine omega naught t, 2 omega naught t, 3 omega naught, and with each up multiple of the frequency, you have a different Cn and a different theta n for each one of them. Yes?
Will this table be provided in like the quiz or the final?
Yes. Yeah, you don't need to memorize this, definitely. Okay? So that's the expression, and according to this expression, you can easily find, but again, it's already provided in that table, that the magnitudes of, the Cn, right? Again, Cn's are real values. So the magnitude of Cn is exactly the same as Cn, okay? Because the Cn's are all real, but the Dn's, no, they are complex, okay? So let's write it again in a more non-confusing way. Cn, because it's always real, is equal to 2 the magnitude of dn, okay? And C0 is equal to D0 directly, okay? And then the phases, theta n, are equal to the angles of the dn. Okay? And this is only for n equals 1 up to infinity. So this applies only to the n's that are positive. We don't use the negative ones, because already the Cn combines the magnitude both of the positive and the negative, and this is why we have the 2 here. Okay, so this relation for n greater than or equal to 1. Okay? The Cn is equal double the magnitude of the complex Fourier series parameters, and the theta, the angles associated, with the compact trigonometric is equal to the angle of, or the phase of dn, okay? So we have the phases here, so we can immediately figure out, again, we only consider the positive side, right? So this positive side is gonna be the theta ends, this phase diagram. That's why it says by inspection, right? So this phase diagram here is simply going to be taken as it is, the positive side of it, and this is going to be your theta ends. So the theta ends is 0 at 0, minus pi over 2 at 1, minus pi over 4 at 2, and 0 everywhere else. This is your theta end. And if you want to get the Cn, again, you take only the positive side here, right, of the magnitude. You keep the DC as is, because in the DC there is no 2 factor. And the remaining ones are all scaled up by 2, multiplied by 2. Okay? You got the idea? So if we apply what I've just said now, let me do it in a very small figure. So going to the Cn, this is going to be 3, this is going to be 1, this is going to be 0. At 0, same. So this is 3. And we say here this is Cn versus n. Okay. And at 1, the value was 2. Now it will become 4. Okay. The value here was 2, right? Okay. The value in this new one is going to be 4. And at 3, the value was 2 root 2. It's going to be 4 root 2. So something slightly higher, 4 root 2. These are your Cn's, just the positive part, including the 0, of the magnitude of dn. But don't forget that all the terms here are multiplied by 2, as we see from the relation, except the DC term, it stays as it is, okay? And the phase, the theta n, is simply going to be this is theta n as a function of n, 0 at 0, and it's minus pi over 2, and at 1, and at 3, it's minus pi over 4, and thank you. That's it. This is your theta n. Okay? So that's how you can get this directly from this by inspection. Okay? Any questions? Typically, if we talk about exams or quizzes or whatever, I'm going to focus on the exponential Fourier series. Okay? If I get you, it's going to be probably one part of a problem that says, after you calculate the exponential, find the compact, for example, and then you will have the table that shows you how to move from one to the other. But I'm doing this example for you so that even when you want to apply that table, you know how to apply it. Okay? So our focus is the complex exponential because that's the more generalized one. You can use it for any signal, and you can get the others from it directly by inspection or mapping, okay, using the table representation. Okay?
Did this question use the table?
Yes, we did, because again, where did I get this relation from? It was in that table, not the table of Fourier series properties, the table that shows the different, the trigonometric and the compact trigonometric and the complex exponential. They were listed in one table, how to calculate each one directly from the signal and the relations between them. If you know one, how you get the other from. Okay? So that's, these relations are in the table. You are not required to memorize them. They are in the table. Okay?
So what's the difference is that in magnitude it only multiplies by 2 and the phase is the same except there's no negative part?
Yes, in both of them there is no negative part. And in the case of the magnitude, except the zero element stays as it is. Because the rationale, so that you don't forget this, or you don't get confused about it, is we wanted to use only the positive side, so where do these energies go? Right? Because they are symmetric, they just simply, we will multiply the ones here by 2. So we can keep the same energy, because all of them should represent the original signal. In this case, it's periodic, so the same power. Okay? So that's why all the factors, all the other elements except at 0, they are multiplied by 2 in terms of the magnitude. But the one at 0 does not have a negative replica, so it stays as it is. Okay?
Doctor?
Yes.
You see how in this example the exponents show exactly which dn it is? Like it's e to the power minus 3j, then it's d minus 3.
Yes.
Would there ever be a problem where it's not very explicit?
No, the only issue is were you able to figure out what's the fundamental frequency by looking at this or not? Because if you didn't see the fundamental frequency, you will get confused what is doing what. Okay? But I mean, I would say in all the cases it should be easily detectable. It's not. I'm not gonna give you something with 1,000 terms, for example, so you get lost. Where is the lowest one? And no, it's like 3, 4, 5 terms maximum, right? Not more than that. Okay.
So which part did you do now? Was it A or
Sorry?
was it the compact trigonometric or no?
Yeah, I did by inspection, find of the spectra in part A, sketch the trigonometric Fourier spectra. So I chose to, because it says trigonometric, doesn't say anything. Then I chose the compact trigonometric. So I sketched them already. And then by having this sketch, can you write them down? Yes, you can. So Cn equals, like C1 is equal to this, C2 is equal to this, and so on, right? Okay. And then show that the trigonometric series found in part B is equivalent to the exponential series of x. Again, I mean, this is a stupid question. You know, I'm never going to ask you this question. No need to show this because they are already coming from the same signal, so they have to be equivalent. Okay?
Yeah.
Find the signal bandwidth. That's an important part. So forget about question 3. It's just a stupid question. I don't know why they have it. And even when you look at the book, when you give the answer for this, the answer says, knowing that both of them are representing the same signal, then they have to be equivalent. So the question doesn't mean much. But find the signal bandwidth. What's going to be the bandwidth of this signal? Again, you can find the bandwidth either from the complex exponential or from the trigonometric. It's the same. So what's going to be the bandwidth of this signal? What is the lowest frequency? 0. Don't forget the 0, right? So the lowest frequency is 0. And what's the highest frequency that it reaches? You only look at the positive side. 3. So the bandwidth of this signal is going to be 3 times omega naught. Don't forget. Right? So here, luckily, omega naught is equal to 1. But if omega naught was equal to 10K, then it's 3 times 10k. Okay? Because what we list here is n, but don't forget when we plot this against frequency, it's n omega nodes. So it's omega node, 2 omega node, 3 omega node, 4 omega node, and so on. Okay? So in this case, the bandwidth is equal to 3. Bandwidth, I want to write it within the white space, okay. Bandwidth is equal to largest, max, n minus min n, and then this whole thing is multiplied by omega naught. Don't forget that. But here in our case, omega naught is equal to 1. Okay? So it's equal to, when I say max n, the maximum n that has a non-zero value, right? Because there are other n's here, but they all have a 0 magnitude, so they don't really exist, okay? So the max is gonna be 3, and the smallest is 0, and then this is multiplied by 1. So the bandwidth is equal to 3, and you can safely write 3 hertz if you want. We will just keep it 3.
What would, can you give an example of what C, for example, C3 would be? If they're writing it down.
Sorry.
If they're writing it down like this.
C3?
Yeah.
It's just simply this value.
Or 2.
These are the C's directly, right? C does not have a magnitude and a phase, it's just a magnitude. And theta is just a phase, so nothing. If you want to write it down, if you want to write like the full Fourier series expansion, you would write it this way. Let me answer that question and then I'll come to you. So if you want to write x of t using the compact complex series expansion, is going to be equal to C0. C0 is equal to 3 plus C1. What's C1? It's 4, right? Multiplied by cosine, right? And then what's inside the cosine? 1 omega naught t, right? Omega naught is equal to 1, so that's t, plus the first angle, right? This guy, theta 1, right? So it's rather than plus, it's going to be minus pi over 2. And then the next term is going to be the 3 term, right? This one, okay? And that's equal to, the value is 4 root 2 multiplied by cosine, and then we have t. Is it t or something else? 3t, because it's n omega naught, right? And now we are talking about C3. So n is equal to 3, right? So the cosine will not have t, it will have 3t, right? And then the angle associated with that, which is theta 3, which is minus pi over 4. And that's it, right? Because in the trigonometric, we don't have negative sides. It's only positive. So 0, 1, we don't have 2, and then we have 3. That's the magnitude, and that's the phase of 3. So that's how you write the compact expansion completely, okay? Any other questions? Any confusion? If you have any confusion, ask.
Yeah, the 4 before the cosine is the magnitude of this.
The 4 before the 4 root 2, you mean here? Or
Yeah.
this one?
Yeah, that one.
The 4 is
The magnitude.
C1. Because the expression says what? Cn multiplied by cosine n omega naught, right? So we have the Cn's here. This is C0, C1, C2 is equal to 0, C3 is equal to 4 root 2, C4, 5, 6, and so on are all equal to 0, right? So just what I wrote here is just that expression up there, okay? With substitution of the actual values. Any other questions?
Yeah, you said that n should be the maximum with non-zero value. So why did we consider a minimum n?
We have the minimum, which is in this case, the minimum with non-zero is 0. There's nothing, we cannot go into the negative, right? Because we're looking at this one. Or generally, when we consider the bandwidth, we only look at the positive side. Maximum means the maximum n, not the maximum value.
The maximum n?
Ah, yes. So I mean the maximum n and the minimum n. The highest n that has some non-zero magnitude and the smallest n that has non-zero magnitude. Okay? Because again, I have n equals 4, 5, 6, but there is no magnitude there. They are all equal to 0 there, right? So you keep scanning until you stop having any more magnitudes. That's your highest n. The location is what you are looking for. For the bandwidth, you are looking for the location. It doesn't matter what's the magnitude as long as it's not 0. Okay? Same when you are looking for the smallest. Sometimes the signal does not have a DC. Right? So in that case, it would have been from here to 3 only. If it doesn't have a DC. Sometimes the signal does not have the DC or D1. It only has D2, D3, D4, for example.
So if it has one value
Hmm?
So if it has one value on
Then the bandwidth of that signal is 0.
0.
Yeah, because it's just a pulse. Doesn't have a bandwidth. It has a frequency component, but it's a single. It's like telling me what's the bandwidth of a single cosine. It's 0 because it has only one frequency. It doesn't have a range of frequencies, right?
I didn't quite get how we got omega naught.
By inspection, by looking up there,
So if there
the e to the j is supposed to be e to the j n omega naught t, right? Now we have e to the j_t, right? N is always integer. So let's assume that because that's the lowest one that we have. And then we have e to the j 3t, and maybe some other expressions have 5 and 6 and 7 and so on, right?
So if we had e to the power of -2t, and that's the lowest that would be, in that
But
case with
again, for any real signal, you will have the negative and the positive. We are not dealing here with time domain complex signals.
so if it's -2 and +2,
You will have always the positive 2 as well.
so in that case omega naught is 2.
If
That's
the
the
lowest that you figure out there is 2, then that means that omega naught is equal to 2. Okay? Because you assume that that lowest one is the one with n equals 1. Okay? Any other questions? Okay, let's go to the next one. Find the exponential Fourier series for the signal, which is given down there, and then using the results. So the first one is for the signal, which is the triangular signal, right? Okay. So find the exponential Fourier series for this one. So D0, 1 over period integration over 1 period x of t dt, and dn is equal to 1 over 1 period integration over 1 period x of t e to the minus j n omega naught t dt. First of all, by inspection, omega naught is equal to, so this signal is periodic with a period equal to 8, right? Because it's from -4 to 4, and then the same thing repeats over and over again, right? Right, so if you look at it, it's periodic with a period equal to 8. So if that's the period of the signal, what's going to be the omega naught for this signal?
1 pi over 4.
Hmm?
Pi over 4.
Yeah, so it's 2 pi over the period, which is 8. So that's equal to pi over 4. This is your omega naught, okay? And now your period is from -4 to 4. I think that's the easiest to use for solving the integral. But again, even if you use from 0 to 8, you are going to get the same thing. Negative sloped line followed by a positive sloped line, okay? So let's just do the integration. So let's do D0, okay? 1 over 8, that's the overall period. And then integration from -4 to 4, but we have 2 parts for that integral. Now we are more experienced, so we don't need to write everything and then break it down. Let's just break it down immediately. So from -4 up to 0, and then another integral from 0 up to 4. For the first integral, what's the equation of the line going through? It's a positive slope line. It crosses the y-axis. So first of all, what's the slope of that line? We know that it's positive sloped. What's the slope?
half. Is it a half?
No, it's 4 versus 1, right?
No, it should be 2
So,
versus
Right.
sorry,
Versus one.
no, not 4. It's actually 4 versus half. No, no,
Oh.
it reaches 1 there, right? I can't see the figure clearly. This is 1, right? And this is 1, right?
Yeah.
So when it spans 4, no, it's the y is 2, you're right. And the x is 4. So the slope of that line is
Rise over.
half. The y over the x. So the slope is half. So it's half. And then multiplied by so it's not going through 0. So it has to be shifted by a value corresponding to or comes or can be calculated from the y-intercept or the x-intercept, whichever you like, okay? So at t equals 0, what's gonna be the y-intercept? Yeah. So in that case, the half t and then plus 1, minus 1, plus 1. Okay. Everyone agrees that this is the equation of the line? Let's try to make sure that we did something correct, right?
From 0 to 4 and then 4 to 8.
Sorry?
We can still do from 0
Yeah, you're gonna have go through the same thing, but it's gonna be a slightly different equation because the shift is different, okay? But we give you the same result at the end. So now if you look at this line, the positive slope line, and we got the equation, we think it's half t plus 1 by, again, substituting values. So let's see actually if this is true. And if I go to that equation and I plug t equals minus 4, what do I get?
Negative 2 plus 1.
Yeah.
Negative 1.
So if I, so
Negative 2 plus 1 gives you negative 1.
yeah, so negative 2 plus 1 gives you negative 1, which is what we have there. And then if I plug into that equation, or I try to see where it cuts the x-axis. So half t plus 1 is equal to 0. This will give you the cut of the x-axis. Where does it cut the x-axis? X-axis is negative, not
Oh, yeah,
Negative
negative
2.
negative 2,
Yeah.
right? So it cuts the x-axis at negative 2, which is what we see there, middle between minus 4 and, just double checking, so middle between this and this, right? Minus 4 and 0, and it cuts actually at minus 2. So that's correct. So now we kind of verified that our equation is correct. That's the equation. This is your x of t, right? And then you integrate with respect to time. The other one is a negative sloped line. So it's minus half t. Already we know that it's the same slope, but negative. And it cuts the y-axis at the same location, 1. So it must be also plus 1 when t is equal to 0. And then you integrate with respect to time. Now you can solve this to get the d0, okay? Do you want to solve it all the way?
Can we move?
No. Okay. And now dn. Same thing, the equations are the same. The only thing is that your integrals, so don't forget 1 over 8 here, and you integrate from minus 4 to 0. It's the same line equations, plus 1, but you have now the annoying e to the minus j n, okay? And then omega naught, just a minute, pi over 4, and then t, and you integrate with respect to time. Yes?
In D0, the 1 out of 8 is in parentheses to the whole thing. Right?
Yes, and both of them. Okay. And the same for the other one. 1 over 8 is completely outside, so it applies to both integrals, both halves of the integration. From 0 to 4, and you have minus half t plus 1, multiplied again by the annoying e to the minus jn pi over 4t dt. Now again, when you want to solve these integrals, you will encounter a part that has t e to the power t, and that part will require integration by part. So solving this also takes a little bit of more time to do, okay? But again, I'll post the final answer for you. When you are trying to resolve this part, you will have to integrate by part when it's multiplied by the e, okay? Now, the question, the second part of the question is very interesting. It says now, if you have found the Fourier series for this. Okay, so now, by continuing here, we should get the dn, which is for this signal. Okay? So now we have the dn for this signal. The question is, can you find the dn for this one without going through the derivations again?
Shift on.
Yes, because you will notice, yeah, exactly. You will notice that this signal, which is already mentioned in the question, is just a shifted version from the upper one. Just shifted to the right. Okay, so if I call this x of t, then this must be x of t.
It's at 2, it was at 0. So plus 2.
Hmm?
Minus 2.
Minus 2.
So every t replaces.
Or you can think of it as shifted to the left as well, right? But in that case, it's a bigger shift.
Yeah.
Because it's periodic. So if you do it on one direction, you can do it in the other direction. But anyways, it's easier to just, because that's the closest one. It's just not so far a shift. So you can think of it as shifted to the right. And it's x of t minus 2. Remember, when you shift a signal, now we go back to the table of properties of Fourier series. Okay? When you shift a signal in time domain, what happens in its Fourier series expansion in frequency domain?
Multiply by e to the j and omega, no, just t naught?
Uh-huh. E to the minus j.
And omega
No.
naught, or just
No, there is no
What's
n.
the question?
The question is, when a signal is shifted in time, what happens to its Fourier series expression?
e to the minus j omega naught omega t naught.
Omega dot t.
Omega.
But there is a omega
E to the minus j,
and omega t.
Omega not t.
omega naught. What's omega naught?
Times the times the shift.
The frequency?
Of
No. Okay. The shift here is this. And the shift in this case, we typically call it t naught because that's a shift in time, right? So what's going to be the expression in frequency?
T minus t not instead of just t. And the e to
no,
the power.
that's in.
The dn, the expression of the dn, what's going to happen to those dn's? They are going to have a phase term. What's that phase term? You are close to the answer. It's e to the minus j.
Omega,
Omega
t
t
naught.
naught. T minus t naught.
Where is omega? What omega?
The omega of this
Pi over.
this signal.
You mean omega naught of the signal? What's omega of the signal?
Yes,
This is
the-
a periodic signal, so we don't have
Yeah.
a continuous omega.
Oh.
Continuous omega happens for Fourier transform. This is a Fourier series, right? So it's dn. So if you have x of t, and that corresponds to dn, then x of t minus t naught will have the same dn, but it is multiplied by e to the minus j. Just the time shift becomes a phase shift in frequency. There is no n associated with it. The shift does not change with the n.
What
It's
about
in the
the
table.
omega?
What does it say?
We just get rid of the n.
E to the max, sorry? No, that's the relation. Shifting, right? E to the minus j, sorry. N omega naught, I am the one who did it. E to the minus j, t naught, n omega naught, you're right. Okay?
In this case, the omega naught is the same as the previous.
It's the same omega naught of the signal because we didn't change the frequency. Shifting it is not going to change the frequency. Okay, so e to the minus j t naught and omega naught. Okay. So if the shift here is 2, this is going to be e to the minus j 2 n omega naught multiplied by dn. Okay. The next one says it's this signal, you can think of it as a time-scaled version of the upper one. Okay, so this one is a time-scaled version from the original one. And the time scaling here is equal to, so So is it x of t over 2 or x2t or x3t, 0t? So it became 2t. So this is going to be x2t. Again, from that table, it tells you that if you have time scaling, there is a expression for time scaling.
1 over a no.
Not scalar multiplication, time scaling.
It's gonna be 1 over the magnitude of A.
I don't think the table has the time scaling, right? It's not
You
listed in
mentioned
the
it.
table. I think we discussed the time scaling only for the Fourier transform. Okay. So anyways, it's going to be, if you do that, your omega naught in this case is going to change, right? When you do this, your omega naught is going to change, right?
It's gonna be, would it be omega over A?
Omega over,
Or is that for omega Fourier transform?
that's for the Fourier. It becomes omega over A, but here, your omega naught is going to change. Okay, so the change of omega naught by itself, so it stays as the same expression, but your omega naught is going to change. Okay?
You were telling her that this is series we're doing, we are talking about transform, but it doesn't matter because it's periodic, no? So it doesn't matter which we use. Yeah.
لا احنا we did not wait for the next lecture to see how we deal with the periodic one from a Fourier transform point of view. So far, periodic signal, we have been only dealing with it from a Fourier series representation, right? Yes, you can do a Fourier transform for a periodic signal, but it will give you something mathematically different.
So these formulas,
It is correct, but it's going to be different. You will see what happens when you deal with periodic signal.
these formulas are for Fourier series representation of a time signal. All the
Of a
formulas.
periodic time signal,
All
because there
the
is no
formulas.
Fourier series for non-periodic. It's only valid for periodic signals using Fourier series representation. Now later on we have the more generalized case, which is the Fourier transform, and it can be applied to both periodic and aperiodic, right? We already studied it for the aperiodic case. The periodic case is a special case inside the Fourier transform. Yeah, so the rules applies, but you cannot use the dn if you want to use the Fourier transform. The expression is different from the dn that we have. Okay? As long as we are dealing with the dn, we are dealing with the Fourier series. Okay? Did we finish time of the lecture? 5 minutes remaining.